In this final outcome, we see electricity and magnetism working together in real devices. We'll go from moving coil meters and the DC motor through to generators, transformers, and eddy currents. Let's begin. Here's what lies ahead. We'll see how electricity and magnetism combine to drive real engineering devices. We'll meet meters, galvanometers, ammeters, and voltmeters with their shunts and multipliers. We'll study the DC motor in its series and shunt forms and link electromagnetic induction through Faraday's and Lenz's laws to the idea of back EMF. Then we'll cover generators, the induction coil, transformers, and eddy currents, always aiming to describe an application and relate it back to the theory. Let's set out some terms first. Magnetic flux density, B, is the strength of a magnetic field in Tesla. Torque, the Greek letter tau, is the turning effect of a force equal to force times distance in Newton meters. The EMF, or electromotive force, is the voltage a source produces in volts. Full-scale deflection is the largest current or voltage a meter is designed to read, and the coil resistance, Rg, is the resistance of a meter's moving coil in ohms. Let's look inside a moving coil galvanometer. A rectangular coil of fine wire is pivoted between the poles of a magnet, and curved pole pieces together with a soft iron core create what's called a radial field. Hairsprings feed current into the coil and also provide a restoring torque, while a light pointer sweeps over a calibrated scale. It's a sensitive instrument, able to detect and measure very small currents, from microamps up to milliamps. So how does it actually work? The current in the coil sits in a magnetic field, so a force acts on it, force equals BIL on each side, and together these give a deflecting torque. That clever radial field keeps the torque constant whatever angle the coil turns to. The coil deflects until the spring's restoring torque exactly balances the deflecting torque. And because of that balance, the steady deflection ends up directly proportional to the current, which is what makes the scale easy to read. On its own, a galvanometer can only carry a tiny current safely. So to make an ammeter, we add a low-value shunt resistor in parallel with the coil. Most of the current then bypasses the delicate coil and flows through the shunt instead. Since an ammeter goes in series with the circuit, it needs a very low resistance overall. The shunt value comes from a simple formula. The shunt resistance equals the galvanometer current times the coil resistance, divided by the difference between the total current and the galvanometer current. Let's size a shunt. Our galvanometer gives full-scale deflection at 5 milliamps and has a coil resistance of 20 ohms, and we want it to read up to 5 amps. The current through the shunt is the total minus the galvanometer current, so 5 minus 0.105, which is 4.995 amps. The voltage across the coil at full-scale deflection is 0.05 times 20, that's 0.1 volts. The shunt must carry 4.995 amps at that same 0.1 volts, so its resistance is 0.1 divided by 4.995, which is about 0.02 ohms or 20 milliohms. To measure voltage instead, we add a high-value resistor in series with the coil, called a multiplier. Its job is to limit the current to the coil's full-scale value even when a large voltage is applied. Because a voltmeter connects in parallel across a component, it needs a very high resistance so that it draws hardly any current from the circuit it's measuring. The multiplier value is the voltage divided by the galvanometer current minus the coil resistance. Let's size a multiplier for the same galvanometer, 5 milliamps and 20 ohms, this time to read up to 10 volts. The total resistance needed is the voltage over the galvanometer current, 10 divided by 0.05, which is 2000 ohms. The coil already supplies 20 ohms of that, so the multiplier is 2000 minus 20, giving 1980 ohms. That series resistor turns our meter into a 10-volt voltmeter. Let's compare the two instruments. An ammeter measures current, connects in series, and has a very low resistance thanks to its shunt, so ideally it would have zero resistance. A voltmeter measures voltage, connects in parallel, and has a very high resistance thanks to its multiplier, so ideally its resistance would be infinite. Getting those connections the right way round matters. An ammeter in series, a voltmeter in parallel. Now to the DC motor, which turns current into motion. A current-carrying conductor in a magnetic field feels a force. Force equals BIL. In a motor, the two sides of a coil carry current in opposite directions, so the two forces act as a couple and produce a turning torque. In this way, the motor converts electrical energy into mechanical rotation, and you'll find them in fans, pumps, trains, power tools, and electric vehicles. Let's look at how a DC motor is built. The armature is a coil wound on a laminated iron core. Field windings, or permanent magnets, supply the main magnetic field. The clever part is the split ring commutator, which reverses the coil current every half turn, with carbon brushes pressing against it to feed the current in. That regular reversal is essential. It keeps the torque acting in the same direction, so the motor keeps spinning the same way rather than stalling. DC motors come in two main types. In a series wound motor, the field winding is in series with the armature, which gives a very high starting torque, though the speed falls sharply as the load grows, ideal for cranes, hoists, and traction. In a shunt wound motor, the field winding sits in parallel with the armature, giving a lower starting torque but a nearly constant speed as the load changes, which suits lathes, fans, and conveyors. Here's a subtle but important effect. A running motor's coil is itself rotating in the magnetic field, so it acts like a generator and induces an EMF that opposes the supply, exactly as Lenz's law predicts. We call this the back EMF. The armature current is the supply voltage minus the back EMF, all divided by the armature resistance. At the instant of starting, the back EMF is zero, so the starting current is very large, but as the motor speeds up, the back EMF rises and reins the current back in. Let's calculate a back EMF. A DC motor runs on 240 volts with an armature resistance of 0.5 ohms, and when running steadily, it draws 20 amps. The voltage across the armature resistance is the current times that resistance, 20 times 0.5, so 10 volts. The back EMF is the supply minus that, 240 minus 10, giving 230 volts. And notice, at the moment of starting, with no back EMF, the current would be 240 over 0.5, a huge 480 amps, which is why motors need starting protection. Let's pause for a check. Why is a shunt a low resistance, while a multiplier is a high resistance? Can you explain why a series motor gives such a high starting torque? And what would happen if a motor had no back EMF at any speed? Have a think before moving on. Now, to electromagnetic induction, the reverse of the motor effect. A changing magnetic flux through a coil induces an EMF, and the faster the flux changes, or the more turns you have, the larger that EMF. Faraday's law puts it precisely. The induced EMF equals the number of turns times the rate of change of flux. The flux, symbol phi, is measured in Webers, and N is the number of turns. This one principle underlies generators, transformers, and induction coils alike. Faraday's law tells us the size of the induced EMF, and Lenz's law tells us its direction. The induced current always flows so as to oppose the very change that produced it, which is really just conservation of energy in disguise. Push a magnet into a coil and you feel it push back, and the work you do against that opposition becomes electrical energy. That's what the minus sign represents in the equation. EMF equals minus N times the rate of change of flux. Let's calculate an induced EMF. A coil of 200 turns links a flux that changes from 0.02 Webers to 0.05 Webers in 0.1 seconds. The change in flux is 0.05 minus 0.02, which is 0.03 Webers. The rate of change is that divided by the time, 0.03 over 0.1, giving 0.3 Webers per second. Then the EMF is the number of turns times that rate, 200 times 0.3, which comes to 60 volts. Generators put induction to work, and there are two flavors. An AC generator, or alternator, has a coil rotating in a magnetic field, connected through two slip rings and brushes, so its output reverses each half turn, producing alternating current. A DC generator, or dynamo, works on the same rotating coil principle, but instead of slip rings, it uses a split-ring commutator, which reverses the connections at just the right moment to give a current that always flows one way. The induction coil is a neat device for producing high-voltage pulses from a low-voltage DC supply. A primary coil of just a few turns carries an interrupted current, switched on and off rapidly by a make-and-break contact. Each sudden change of flux induces a large EMF in the secondary coil, and because that secondary has very many turns, the result is a high voltage. Historically, these were used in ignition systems and to generate sparks. The transformer is one of the most important applications of induction. Two coils share a common laminated iron core, and an alternating current in the primary sets up a changing flux, which in turn induces an EMF in the secondary. The turns ratio sets the voltage. The secondary voltage over the primary voltage equals the secondary turns over the primary turns. More turns on the secondary steps the voltage up, fewer steps it down, and for an ideal transformer power is conserved, so the primary voltage times its current equals the secondary voltage times its current. Let's work a transformer example. It has 800 primary turns and 200 secondary turns, with 240 volts on the primary. The secondary voltage is the primary voltage times the turns ratio, 240 times 200 over 800, which is 240 times 0.25, so 60 volts. If the secondary delivers 5 amps, the secondary power is 60 times 5, that's 300 watts. Assuming it's ideal, the primary power is also 300 watts, so the primary current is 300 divided by 240, which is 1.25 amps. Finally, eddy currents. When a changing flux passes through a solid metal core, it induces little swirling currents within the metal itself. These eddy currents waste energy as heat and reduce efficiency, which is a problem in transformers and motors. The cure is to laminate the core, building it from thin insulated sheets, which raises the resistance to those circulating currents and cuts the losses right down. That said, eddy currents aren't all bad. We put them to good use in braking and in induction heating. Let's gather the key terms. A commutator is the split ring that reverses the coil current every half turn. Back EMF is the induced voltage in a motor that opposes the supply. The turns ratio is the ratio of secondary to primary turns. A step-up transformer has more turns on the secondary, giving a higher voltage. An eddy current is a circulating induced current in a conducting core, and lamination means the thin insulated core layers that cut those eddy current losses. One last check. Can you state Faraday's law and Lenz's law in your own words? If a transformer has more secondary turns than primary, is it step up or step down? Why are transformer and motor cores laminated? And can you give one useful and one wasteful effect of eddy currents? Give those a go.
Some final key terms. An energy level is one of the fixed, discrete energies an atomic electron may have. The ground state is the lowest energy level, where the electron normally sits. An excited state is a higher level occupied after the atom gains energy. The ionization energy is the energy needed to remove an electron completely from the atom. And activity is the number of nuclear decays per second. measured in becquerels. Let's finish with a check. Can you state the difference between excitation and ionization? If a photon has less energy than any level gap in an atom, what happens to it? And if a sample falls to 1/16th of its activity in 8 days, what's its half-life?